Alright, so what we were saying was the cutoff frequency. So what is the cutoff frequency in this case? Well, you've got the whole line of the open system L, and the cutoff frequency is where the magnitude of your transfer function, so the frequency at which the magnitude of the transfer function is 1. How many decibels is 1? It's a gain of 0 decibels, right? So if you imagine you draw a line here at 0 decibels, and you check the frequency, then you fall about here probably, this is around 30 radians per second. So in fact, if you do it in MATLAB, you get a more precise result, and it turns out to be 30.66 radians per second. So that's a crossover frequency. So you choose a sample frequency to be 20 times the open loop bandwidth or crossover frequency. And I did the math for you. This corresponds to a sample time of 0.0102 seconds. So if you use this sample rate, you substitute t into here, and you get the transfer function for the discrete controller. Then what you do is you create a model for the plant, G of S, preceded by a zero repose, because you want to have an entirely discrete system. So this is exactly what we've seen before. You apply the formula that you have seen, and you get the equivalent of the plant. And at this point, you have the full closed group system with the plant preceded by zero repose and the discrete controller, everything in a closed group transfer function. And this is the result. If you plot the poles in the complex plane, the poles are here. Now, you may know that in the complex plane you can draw lines that are in fact curvy lines that represent constant natural frequency and constant damping. Have you seen such a plot? Yes? If not, then I remind you quickly. Something like this. So the blue lines represent constant omega. At point 1, you have omega equal to 0. And at point -1, you have the maximum frequency that a digital signal can represent, which is pi over t. That's the Nyquist frequency. Right? Instead, the red lines represent constant damping. The unit circle is damping equal to 0, because if you have a pole on the unit circle, you have a sinusoid of constant amplitude, not damped. But when you go inside the unit circle, the damping increases, and then on the line 0 to 1, this line here, the damping is equal to 1. So it's the maximum damping that you can possibly achieve. Right? Have you seen this plot before? Yes, good. So this plot is exactly what you see here, except that there are no colored lines. But the numbers that you see here is the value of the damping, and the numbers that you see here is the value of the frequency. And the poles are here. Now, if you look, for example, at the line of the damping crossing this pole, you will see that it's pretty close to 0.7. Right? The 0.7 was the damping that we had assigned before. The natural frequency we assigned before was 25, and if you do the maths here with t and the sample time and pi, it turns out that this one is actually pretty close to 0.225 radians per second. So the poles are pretty much in the right place. And you can see that the poles are in the right place if you try to do a step response of the system. This plot is a comparison of the step response of the continuous system but is pretty much close, right? Okay, now the last thing I want to show you, and then I'll let you study this worked example yourself, is the following. What if you can't decide the sample time freely, and you can't decide to keep a sample frequency that is 20 times higher than the frequency of the system? You're only limited to 6 times the open loop value. So the sample time is much larger. Why would you have such a case? Well, it happens if you have to use a computer that you already have. So you can't decide sample time, that's the one you have, the hardware is already there. So in this case, if you set the sample time to be that, you apply the controller again, you rederive it, the poles go in here, here, and here. As you can see, they move quite far away from where they used to be before, right? That's because the sample time is too large. If you plot again the step response, you get something like this. So in this case, the overshooting is well beyond the specifications that we had before. So this control is probably not acceptable. What can you do to overcome this limitation? Apart from buying a new computer with a higher frequency. What is the problem? The problem is that the tasking rule has moved the poles somewhere else. When you apply the tasking rule, the poles have moved from the position where you wanted them to be with a certain damping and a certain natural frequency to a different place. So what you can do is to simply replace the poles in the digital domain using this graph, putting them exactly in the position where you want them to be. So if you know the damping and the natural frequency, you know the position of the pole, so you place the pole in this graph, and then you literally measure where the pole is. And if you do so, you end up with a closed loop transfer function that looks like this one. These are the poles. I change the value, and you get again the constants for your proportional and integration coefficients. And then you do the step response again with the same sample time, so the large sample time, but you get something like this, which again still has got some overshooting, but is in no way comparable to the one. So we have improved quite the performance of the digital controller, even if the sample time is rather large, by moving towards ourselves where we want to be. So I'll let this to you. If you're interested, just have a look, and more detailed description is in the document itself. What I'm going to do now, upon request of some of you guys, is to go through one exam script. Okay? And the one I picked is December 2014. If you don't mind, I start from numerical exercises. That is section B, which is probably the one that requires more explanation if you want. I think the theory you can find in the notes, but we can go through the theory as well if we have time later. question 3a says, consider a continuous transfer function of a low-pass filter with cutoff frequency minus 3 dB of 10 radians per second. Would you know how to design this filter? No? Okay. So this question is, this part of the question is not digital control. We are designing a continuous transfer function, okay? Okay, so it's a low-pass filter. So the Bode diagram, omega and magnitude should be something like this. Correct? And ideally, it goes like that. This frequency here, that's the cutoff frequency. Right? Why is this like this? It's not me. So, the definition of the cutoff frequency is the frequency at which the gain is minus 4 dB. So, this bit is minus 3 dB. So, the gain has decreased by 3 dB with respect to the steady state gain. I don't say it here in the question, but the easiest filter that you can pick is a first order low pass filter, right? A first order low pass filter has a transfer function that looks like 1 over tau s plus 1. Let's see, I start. Usually the start solves 99% of the problem. Alright, so that's the typical form transfer function of a low pass, first order low pass filter. Tau is the time constant and is related to the frequency as tau is equal to 1 over omega. So the transfer function, if you want to write it as a function of omega, can be written as omega over s plus omega. If omega is the cutoff frequency, then I call it omega bar to be consistent with my plot here. Okay, do you really want to see that this is a low pass filter that we wanted, that the cutoff frequency is minus 3 dB at omega bar? If you want to see it, then what you need to do is to calculate the frequency response of this. No. We have the 1% time. I used the same thing yesterday and the day before.
Oh, così trovando.
So how do you compute the frequency response of J, of G? when you evaluate G in J omega, right? If you want to know the frequency response at the cutoff frequency, then you evaluate in G omega bar. And you want to compute the magnitude of this. So the magnitude of this is the magnitude of omega bar over J omega bar plus omega bar, which is equal to the magnitude of 1 over J plus 1. What is the magnitude of this complex number? 1? I heard of 1. Well, I find it difficult to compute magnitudes of complex numbers in general, but they are especially difficult when the complex number is at the denominator. Okay, so you want to bring it at the numerator. So what you do is to multiply by j minus 1. So the denominator you get j plus 1, j minus 1, right? Which means that the denominator becomes j squared minus 1. And j squared is minus 1. So this is j minus 1 over minus 2. Or is 1/2 the magnitude of j minus 1. What's the magnitude of j minus 1? Square? Yeah? No? I heard something. What's the magnitude of j minus 1? Square root of 2. So this is square root of 2 over 2. Which is 0.7 something.
complex number
And that's exactly what we wanted. If you compute it, sorry, not the magnitude, but the magnitude squared, because that's the power. So the magnitude squared is square root of 2 over 2 squared, which is 1/2. So the power has decreased by 1/2 at omega bar. And that's exactly the definition of the cutoff frequency, 4 minus 3 dB.
This one has square. DJ omega square. What do you say?
This is not really needed for the exam script, right? It's just for you to show how it works. For the exam script, I am assuming that if I say design a continuous transfer function, that's the design. You just put down here, you put omega equal to 10 radians per second, and that's it. So now we have it. So our transfer function for the actual exam script is g of s equal to 1 over 0.1 s plus 1. That's the one we're using.
2.1 s plus 1.
Alright, so the first question, the first part of the question, A, says design the discrete equivalent of it using the just considering a sampling time of 0.3 seconds. Compute the gain in dB of the digital filter at cutoff frequency, again, as before, and compare it with the analog version. Alright, so we have QS equal 1 over 1 plus 1. We need to compute the discrete equivalent according to the Tasking rule. We've seen that before, very easy. You do the substitution. S equals 2 over t, z minus 1 over z plus 1. And then you do a little bit of maths, you get 0.6 z plus 0.6 over z plus 0.2.
我看不到。
Now, we need to compute the gain of this new digital filter at the same cutoff frequency, which is omega bar equal to 10 radians per second. How do we compute the gain of this digital filter now? The frequency response we did before is G in J omega. In this case, we have G of Z. Shall I do G of Z evaluated when Z is equal to J omega? No. Shall I do that? No? Why? What shall I do instead? How do you compute the frequency response of a certain discrete system or a continuous system? Well, the way you compute it is you feed the system with a sinusoid. So you put the poles where the poles of a sinusoid would be. So J omega represents the imaginary line, imaginary axis, because the imaginary axis is the location where the poles of sinusoids are. Does it make sense what I'm saying, or no? Okay, so it continues. Why you compute G of J omega? Well, if you draw a complex plane, and you have the imaginary axis here and the real axis here, right? What is J omega in a complex plane? Well, omega is a number, is a frequency, is a real number. J is the imaginary unit. So this is a purely imaginary number, which means it's the imaginary axis, right? So this axis here is J omega, right? And if you place poles on this axis, the distance of the pole from the origin is omega, right? And represents the frequency of the sinusoid that you are trying to represent. Let's see what happens now in discrete. Again, you have the imaginary axis and the real axis. How does J omega map in the discrete Z plane? Where does J omega map in the Z plane? Unit circle. So this means that these two poles of the sinusoid with frequency omega will map into a couple of complex conjugate poles somewhere on the unit circle. Is that correct? Yes. Now, in this plane, the frequency omega is not anymore the distance from the origin. As we have seen, there are lines of constant omega that are not straight lines. They follow certain curves. If you overlap that plot with all the lines of omega, you can actually compute the frequency graphically. But it doesn't really matter because we can compute it analytically. And the way we do that is the following. How do you map a pole from the S-plane to the Z-plane? So the way this one maps is according to the usual map that we know, right? Which is e to the power of st. So this means that if you want to do a frequency response analysis again in here, you need to use g to the power, g evaluated in e j omega t. That's the frequency response to a sinusoid of frequency omega in a discrete system. And by the way, e to the power of j omega t is nothing else but the analytical expression of the unit circle. Right? Do you have any questions on this? Was it clear before? Yes? Okay. So if something is very clear already, just tell me and I'll go faster, okay? If something is not clear, again tell me and I'll slow down and go more into details. Right? Okay, so we need to find the frequency response of our filter here. So now we know what to do. G in e to the power of j omega bar t, where omega bar is 10 radians per second. And I did the math for you, and this is 0.1058 in magnitude. Need to compute the magnitude.
0.1058.
However, we need to compute it in dB, right, decibel. So the magnitude of G in decibel is equal, and you may know the formula for computing magnitude in decibel, is 20 times logarithm base 10 of this number. So of the magnitude of G in E j omega t, which is this number here. And this turns out to be minus 19 dB.
19.
What is the meaning of this? The meaning is that the Tustin rule has changed the characteristic frequency of the filter. It's no more the same. So at omega equal to 10, we don't have a gain of minus 3 dB anymore, but we have minus 19. So our filter is completely different now. It's been distorted by the transformation. So what can we do about this? Well, we can go to point B of the exercise. Here clearly there is a typo because it says twice point A. And it says redesign the discrete equivalent of the filter above, but this time apply a pre-warping such that the gain is preserved at the cutoff frequency, at that frequency. We want to redesign it, but we want that in the discrete filter at 10 radians per second, we still have exactly minus 3 dB. That's the purpose of the filter. Then it says to verify it numerically. So first do the design, and then verify it numerically. So we need to apply the pre-warping. Have you seen the pre-warping in the class? Okay, good. So for the pre-warping, first of all, you need to calculate the pre-warping frequency, which I call A, and is 2 times over T. Sorry, oh, sorry. Excellent, thanks. Thank you. So the pre-warping frequency is A equal 2 times over T tangent of omega T divided by 2. This is 94 if you want the numbers. And then at that point, we say that the discrete filter with the pre-warping is equal to the filter in S over A applying the testing rule. So applying S equal to 2 over T Z minus 1 over Z plus 1. This is the pre-warped transfer function. So we apply the testing rule to the pre-warped transfer function rather than to the original transfer function. But you can also use the shortcut and say, fine, I instead use g of s prime, and I do the substitution s prime equal to omega over tangent of omega t divided by 2 z minus 1 over z plus 1. That's the same thing. Okay? And if you do so, you find, by substituting the numbers, 0.9338 z plus 1 over z plus 0.86 something else. .8676.
So hard to
That's
see.
Z plus 1. Okay? And then it says to verify it. So again, you just need to compute the frequency response of this guy for omega equal to 10. So we do exactly the same as we did before. G evaluated in e to the power of 3 omega t, and we calculate the magnitude. Same way as before, you do the substitution, you put the numbers in, and you get 0.7 or something, 07, and so on. Do you recognize this number? This is very similar to square root of 2 over 2. In fact, if you compute the magnitude of G, E, J omega t in dB, you get minus 3.01 dB. Okay, are there any questions about this exercise? Yeah, no?
叫人头，在作业。
Okay, are there any questions? If not, we go on to the next exercise. Point A, using the zero-pole matching rule, find the discrete equivalent. Select the appropriate parameters such that the discrete transfer function preserves the gain for a constant signal. Then consider a sample time of 0.5 seconds. So let me copy the transfer function here. H of s, then s minus 1 over s squared plus s minus 6. Okay, so this is about pole zero matching. So when you want to do the transformation, the conversion to pole zero matching, the first thing you need to do is to find the poles and to find the zeros, right? So let's start from the poles. What are the poles of this transfer function? Well, it's difficult to see from here. You need to decompose the denominator, right? You need to solve the second order equation. And if you do so, you can rewrite the denominator as s minus 2 times s plus 3. So what are the poles of this thing? S equal to 2 and s equal to minus 3, right? How do the poles map? Should be s minus 3 in here. No, because if you multiply these two, minus 2 times plus 3 is minus 6. And the double product is 3s minus 2s, which gives 1s. Okay. So, how do we map the poles? According to the same rule as orbits, we say z is equal to e to the power of st. And you just put the numbers in, and you get 2.7 something. And then for the second one, you get 0.22. Right? Nothing difficult in here. Zeros. What are the zeros of this transfer function? S equal 1. How do we map it? Same thing. Z equal e to the power of st, and you put the numbers in, you get 1.64. Anything else? Sorry? Infinity, yes, I heard infinity. What infinity? A zero at infinity, yes. So how do you compute the zeros at infinity? Well, what I usually do is I compare the maximum power of the numerator and the denominator, right? So if they are the same power, there is no zero at infinity. If the denominator has one more power than the numerator, then there is one zero at infinity, and then there is one more zero at infinity for each power, additional power that the denominator has. So in this case, the difference is 1, there is one zero at infinity. And where does this map? Z equal to minus 1. Do you know why a zero at infinity maps to minus 1? What's the reason of this mapping? Because we are not following the same rule, we are just saying, okay, it goes to minus 1. Well, to understand, we need again to draw the two complex planes, the S plane and the Z plane, and see what is going on at infinity. Imagine to consider again the imaginary axis here on the S plane, and imagine to have a pole, or a couple of complex conjugate poles, with a certain frequency, omega, but this frequency increases up to very high frequencies, up to infinity. So you imagine to move the pole here until you get to infinity on the imaginary axis. How does the pole move on the unit circle? Well, when the pole starts at the origin, the frequency is 0. Where is the pole in the z plane? At 0 frequency. 1, yes. So the pole starts here at omega equal to 0. And then while the frequency increases in the s plane, what is going to happen to this pole on the z plane? It moves along the unit circle, right? So it moves this way up to here. What is this frequency? No, this frequency is not. This is the point is -1. But which frequency does this point represent? This represents the Nyquist frequency, which is pi over t. And this frequency is the maximum frequency that this digital system can represent. It's the Nyquist frequency. You cannot go beyond this one. You cannot go to infinite frequencies here. Because if you keep going, if you keep moving your pole, what happens is that your pole will go into the bottom side of the circle. But the bottom side of the circle has actually got the same frequency range as the top side of the circle, because it's just a couple of complex poles. So in fact, what you're doing if you keep going is using a sinusoid that has got a lower frequency than what you expect. That's a Aliassime essentially. Right? So if you want to prevent this to happen, what you can do is to say, okay, fine, then why don't we say that the highest frequency of the continuous system maps into the highest frequency of the discrete system. It's not perfect, because the highest frequency of the continuous system is infinite. Instead, here is pi over t, which is finite. But that's the best you can do. Right? So the rationale is that whatever is in this region here of the S-plane should map in this region here of the Z-plane. Because those two regions represent in different ways the maximum frequency. And the result is that you are stretching the full imaginary axis here onto half the circle. So again, this stuff here is not required for the exam. I'm just trying to explain what's behind this mapping. For the exam, you just need to state this. You just need to say that there is 1 0 at infinity, and therefore you put the 0 at -1. Brackets. Alright, so we have poles and zeros, so you get my h of z, which will be z minus 1.6, z plus 1, z minus 2.7, z minus 0.2. Is there something missing? Gain k, which is still to be defined. Now, the text of the exercise says that you want to preserve the gain for a constant signal, which is a signal with frequency equal to 0. That's a constant signal. This might not always be the case. Sometimes you want to preserve the gain at a different frequency. It really depends. Depends on your application. If nothing is said, you choose a frequency yourself. If you want to make your life easier, you choose 0. So what do? Well, you compute the gain in the continuous transfer function and in the discrete transfer function, and you set them to be the same. So you start computing h of s. You want to compute the gain, the magnitude of h of s when s is equal to 0. And if you do the math, you'll get 5/3. And then you do the same for h of z. You compute the gain of h of z at 0 frequency, which means z equal to 1. Good. And this turns out to be 0.97 K. Unfortunately, K stays in. Fortunately, because it's what we want to find. So from these two, we say that these two should be the same. We set them the same, and we get one equation in K. So we get 5/3. 5/3 equal to 0.97 K, and therefore K is equal to 1.714.
就是14，这个是这个是区域。
The last part is it should be straightforward. There's nothing difficult. It's safe to find the corresponding difference equation of the transfer function. So how to convert the transfer function into a difference equation.
很好。
Usually when I do maths, I have to do calculations. I don't like to carry over all the numbers all the time, because every time I have a summation, I have to take my pocket calculator out and do the math. So what I prefer to do instead is to put some letters in and substitute the numbers again. So in this case, I write the transfer function h of z in this form: a z minus z1 z minus z2, where these are the two zeros that we found before. At the moment I just use the letter, over z minus p1 z minus p2, and these are the two poles. And then if you want to find the difference equation, you need to think of the transfer function as a ratio between the output and the input. So h of z is equal, in fact, to u of z, the output, divided by e of z, the input. Equal to the same thing. And then you write it as a polynomial instead of a ratio of two polynomials. So you put the denominators on the opposite sides, and you get u of z, z minus p1, z minus p2, equal to e of z, z minus z1, z minus z2. Then you solve, you do the maths here, and then you anti-transform.
Have a cave
So what the K?
And K, yes, it should be somewhere. Thanks. this would be minus 1 point for me.
Support transformer.
NT.
Transformer.
And then you anti-transform. So I'm not going to write the whole thing because I think it's pretty straightforward, but you will end up with terms of type A, K, E, Z. And when you anti-transform this one, becomes K, sorry, K, small e, K plus 1, right? Because every time you have a multiplication by z, you have a shifting in time when you transform, right? So if you have a term of type ke, this anti-transforms into ke. And if you have a term ke z to the power of minus 1, this becomes ke minus 1, and so on and so forth. So you do the same thing, the same for u. It's just solving and applying the anti-transformation. So I'm not going to do it because it takes some time. It should be easy. Are there any questions on this exam screen? Do you think it's difficult or easy or easy?
Tell me your source now.
You want me to briefly go through the theoretical questions of section
哪个section要做全部啊？A 是全部。B 跟 C 是因为关闭。B 一题 C，B 是一个
做 B 2题而已。
Oh yeah. Now I do.
Define the two main differences of a digital signal with respect to analog continuous one. What are the two features of a digital signal with respect to a continuous one? Can you shout? Yes. I kind of hear, but not really. Yes? What is a digital signal? Quantized, I heard quantized and discretized. Okay, so those are the two features, is discretized and quantized. So first of all, you need to mention these two features. And second, you need to briefly describe what these features are, right? So a discretization is something that happens in time. It means that you have discrete samples of in time and not a continuous function of time. Quantization instead is a discrete set of values for a signal. And this is related to the word size of the computer you're using. If you want to make it visual and help your description a bit, a graph like this would help a lot. So you have time, and you have your signal. Discretized signal is something that is like this, right? Discretized in time. Quantization, you need to show that essentially you have a finite set of values that your signal can assume. So at any certain point, your signal is either one quantum or the next one. It cannot be nothing in between. The number of quanta that you have depends on the type of computer you're using, the architecture. Essentially depends on the number of bits of your processor. So So if you sketch these two things and you say discretization, quantization, and you write a couple of words for each one of the two explaining what they are, that's it. Okay? The second one says state the condition under which a difference equation with no input is stable. Show it by means of a simple example with choice. So what is a difference equation with no inputs? Well, it's something that looks like this. UK is equal to a function of what? Of UK minus 1, the previous step, UK minus 2, the previous step, and so on and so forth, up to a certain order. And that's it. It does not depend on anything else. This encodes a transfer function, which is not really a transfer function because it's just a block that has got an output but doesn't have any inputs. It only depends on the initial conditions. You set the initial conditions and this thing starts to give you values up to infinity. So let's pick one example and show the stability conditions. I pick UK equal to UK minus 1 plus UK minus 2. There's no input, otherwise there would be EK, so there's no input. How do you assess the intrinsic stability of this difference equation? You try to substitute the general solution. The general solution of this is UK equal to AZ to the power of K. If you do the substitution, what you get is a polynomial. Z to the power of K is equal to Z to the power of K minus 1 plus Z to the power of K minus 2. This thing is called a characteristic equation. Right? We can simplify it a little bit because we still have K at the exponent, which we don't like that much. So we divide everything by Z to the power of K, and we get 1 equal to Z to the power of minus 1 plus Z to the power of minus 2. Also, we don't like negative exponents. We prefer to work with positive ones, so we multiply by Z to the power of 2. So we get Z squared equal to Z plus 1. That's now a second order ordinary equation. So we can find the solutions. You know the formula for finding the solutions. I hope we get 1 plus or minus the square root of 5 divided by 2. Now to go back to the question of the exercise, it says what are the conditions for the stability of this difference equation? But the condition is that if all solutions, all is important, all the solutions have magnitude less than 1, then the difference equation is stable. Okay. So what you have to verify is that the magnitude of Z1 is less than 1, and the magnitude of Z2 is less than 1. You verify that, and you see clearly that it's not in this case, because you have 1 plus something else. So You draw your conclusions. Instability here means that essentially there is a set of initial conditions for this difference equation here that makes the value uk to grow to infinity as k grows. If instead the equation was stable, it means that you can choose any set of initial conditions, but uk will never grow to infinity. It will always be bounded. In the last part, which is part C, it says, consider a discrete exponential signal, ek equal to r to the power of k for k greater than or equal to 0, and ek equal to 0 for k less than 0. Find the z transform and show the condition for the stability. So it's essentially an exponential signal. You need to find the z transform and show the stability. So the first thing is to write the signal ek can be equal to two things, either r to the power of k if k is greater than or equal to 0, or 0 for k less than 0. Then you need to find the z transform. And here I apply exactly the definition of a z transform, that is the summation for k equal to minus infinity to plus infinity of ek z to the power of minus k. ek is r to the power of k, so this is the summation of r to the power of k, z to the power of minus k. However, my signal is 0 for negative k's, so I can discard them from the summation and say that the summation starts at 0 and it goes to plus infinity. And then I can collect the power of k and say that this is r, z to the power of minus 1, everything to the power of k. And this is essentially a to the power of k. So a constant, if you want, to the power of k, which means it's a geometric series. And we know that the result of a geometric series is 1 over 1 minus a. So in this case, r z to the power of minus 1. If the norm of a is less than 1, so the norm of r z to the power of minus 1 is less than 1.
Stable.
Or if you multiply by z, you get z over z minus r, which is probably easier to write and see. And the condition here becomes norm of z greater than norm of r. So when is this transfer function, if you want the signal stable? Well, you need to check the poles, right? What are the poles of the signal? R, Z equal to R. So when is it stable? When the magnitude of the pole is less than 1. So the condition for stability is that the magnitude of R must be less than 1. And that's the answer. Okay, I leave the podium for a while now, but I will be available if you have further questions.